The discovery of the Higgs boson in 2012 provided experts with two concurrent opportunities. On the one hand, the triumphant joy of finally having found the last missing particle of the Standard Model. On the other hand, the frightening realization that this very model is incomplete. In fact, the so-called God particle, as it is often mentioned, presents a serious problem, or more precisely, a hierarchy problem. This means that its mass is 100 billion times less than one might expect according to quantum mechanics. One approach to solving this confusing issue is the hypothesis that each particle of the Standard Model has a superpartner, which is symmetric. However, in practice, and this is the crucial point, none of these predicted particles has yet been revealed at the Large Hadron Collider. The Higgs boson is the elementary particle with the most acclaim of all. But what exactly is the Higgs boson, and why is its detection at the Large Hadron Collider one of the most important junctures in the well-organized history of research? To reach the bottom of these exciting questions, we first have to remember that without mass, the universe would, of course, be a completely different place. After all, without it, there would be no atoms and no normal matter. It is indeed only the weight of the elements that make them up that causes the basic building blocks of matter to hold together and interact. But where exactly do elementary particles get their mass from in the first place? That was specifically the mystery that the Standard Model of particle physics was unable to solve for a long time. However, this was not the only problem. Quite the opposite, in fact. The bosons, which mediate the interactions of matter with one another, should theoretically have no mass at all. In contrast to photons and gluons, which serve as the vehicle elements of the electromagnetic spectrum and strong force, bosons with mass simply do not align with our physical understanding. Yet, as one of the four fundamental forces of physics, there is a mediator in the weak interaction, the W and Z bosons, which do have mass. This accounts for the restricted range of the weak interaction, among other things, in the decay of particular radioactive nuclei. However, where the majority of these exchange particles get their mass remained an unsolved mystery for decades. Then came theoretical physicists like Robert Brout, Francois Englert, and Peter Higgs, who, independently of one another in the 1960s, realized that the mass problem could be solved if the entire universe were surrounded by an invisible scalar field. This quantum physical field might interact with some fundamental particles and, as a result, change their properties. In this way, the affected particles would only be able to accelerate by putting out energy, ultimately giving them mass. But why do not all carrier particles have mass? After all, photons and gluons remain massless and move at the speed of light. The so-called Brout-Englert-Higgs mechanism provides an answer to this. Due to its asymmetry, the Higgs field does not interact with all bosons equally. Since it is neutral with respect to electrodynamics and quantum chromodynamics, photons and gluons remain massless. However, the field exerts a kind of braking effect on all other particles, giving them mass. How do you prove such a fundamental assumption? With the help of the Higgs boson. If the Higgs field exists, it must also possess condensations at certain points. Just as a photon embodies both a wave and a particle, the Higgs field can manifest in the form of a particle. The hunt for the Higgs boson was long. According to predictions, it would take nearly 50 years before its existence could be proven. But what made the search for the much-cited God particle so complicated? The fundamental issue was that the key property of the Higgs boson, crucial for its experimental detection, did not emerge clearly from theoretical calculations. The particle was expected to have no spin or charge, but should have mass. However, no one knew its exact size. This posed a serious obstacle in the search. Only if researchers knew the mass of the Higgs boson could they determine the energy levels needed for particle collisions in an accelerator. The possible range was extremely wide, from just 18 megaelectron volts to 800 gigaelectron volts. However, previous particle accelerator experiments had shown that the Higgs boson was probably heavier than 114 gigaelectron volts. When the Large Hadron Collider at CERN became operational in 2008, It opened completely new possibilities for detecting the Higgs boson. However, even for the world's largest particle accelerator, the natural properties of this extraordinary particle posed a challenge. The Higgs boson is produced in only about 1 in a billion proton collisions and decays within a fraction of a quadrillionth of a second. As a result, it can neither be directly measured nor observed, only identified based on the decay products it leaves behind. These decay products, such as photon pairs, muons, or Z bosons, are also released in other particle interactions, making detection even more difficult. Yet, physicists achieved the seemingly impossible task by comparing predicted decay products with experimental data. They checked whether expected curves showed deviations in a specific mass and energy range. Indeed, what emerged on July 4, 2012, as a straightforward hump in the data turned out to be nothing less than the biggest sensation in particle physics. The Higgs boson had been detected in 2 of CERN's massive detectors. This milestone was compared to the discovery of a new continent for science. However, the truth is that this continent still has many unexplored regions. Why is the existence of the Higgs boson so mysterious? As mentioned earlier, there is a serious problem regarding its mass. The Higgs boson has a mass of 125 gigaelectron volts, which is 13 orders of magnitude smaller than the Planck mass, the fundamental mass scale in quantum mechanics. From the perspective of the Standard Model, there is only one explanation: an extremely unlikely coincidence between the fundamental building blocks of the universe. This coincidence is so improbable that physicists refer to it as the hierarchy problem. It suggests that our Standard Model is missing something crucial. Some unknown mechanism must explain the unexpectedly low mass of the Higgs boson. For a long time, supersymmetry was considered the most promising solution. This theory assigns a heavier superpartner to each Standard Model particle, creating a mirror structure. Before the Large Hadron Collider became operational, proponents of this theory expected to find a flood of these so-called SUSY partners. However, to this day, none have been found. This is particularly frustrating because, on paper, supersymmetry provides an elegant solution to the hierarchy problem. Interactions with these superpartners could influence the Higgs field, and models predict additional heavier Higgs bosons. These could explain why the currently known Higgs boson has such a low mass. So why haven't these superpartners been detected? One possibility is that supersymmetry simply does not reflect the real world of particles. Alternatively, some physicists suggest that the solution lies in a hidden sector, a family of particles that interact among themselves but are completely unaffected by electromagnetic and weak interactions. If this is true, these particles would not interact directly with ordinary matter, making their detection extremely difficult. Some experts propose that particles in the Standard Model try to pull the Higgs boson up, making it heavier, while particles from the hidden sector pull it down again. This would mean the Higgs boson can escape into this hidden sector, transforming into an exotic twin. Whether this theory is correct, and whether we will ever gain insights into this hidden sector, is still uncertain. Nevertheless, scientists are not giving up. After all, it took nearly 50 years from the theoretical prediction of the Higgs boson to its experimental detection. The research world remains determined to uncover the next great breakthrough in our understanding of the universe.